Good evening and welcome. Tonight's talk, entitled New States of Matter, is being given by Professor Mark Warner, who is a Fellow of the Royal Society. Professor Warner is one of the founders of the fields of liquid crystal elastomers. He has pioneered much of the statistical mechanical understanding of polymer liquid crystals. His work has inspired experiment and theory in a large number of groups internationally in chemistry, physics, mathematics, engineering, and industry. They are pursuing novel mechanics, photoactuation, rubber lasers, and optically driven ferroelectric rubber. Today, Professor Warner will demonstrate that putting solids and liquids together in a novel way can produce new substances that apparently defy Hooke. He will illustrate that once the rules are stretched, fascinating new phenomena can emerge. Please join me in welcoming Professor Mark Warner.
Well, thank you, and it's a great pleasure to be here tonight. I want to relate a story about searches in Cambridge and in other places for new states of matter. And by new, I mean new according to an ancient classification that goes back to the hero of this evening, Robert Hooke, who's been called England's Leonardo. I'll say a bit about him as we go along. But to get started, we'll have to talk about liquids, solids, and gases, and then I'll talk about some curious substances, and then about breaking the rules that Hooke laid down so clearly a long time ago, and where is it leading. I'd like to say at the outset that most of this work, the theory and the experiment that you will see, has been done with a fabulous, very able colleague of mine in Cambridge, Professor Terentiev, and I'm actually delighted to see in the audience another colleague of mine, James Adams. So it's a great pleasure to be able to present their work. So here is our hero. This is Robert Hooke, or at least a person whom we think is Robert Hooke. And it's on the cover of a wonderful book by Lisa Jardine about Hooke. And as I've read more about him, he becomes more and more a hero of mine for reasons that I think you'll begin to see. And also, there's a book by Alan Chapman called England's Leonardo, and that's an essay that you can find on the web based on his book. Both are most compelling reading. So Hooke, he was born in 1635 on the Isle of Wight. His father was a clergyman, and he went eventually to school in London and then to Oxford, and he worked in Oxford after his studies as an operator for Boyle. That was somebody who helped Boyle with his experiments on vacuum and on air and the fundamentals of nature that they were beginning to unpick at that time as the Enlightenment was starting. And Hooke and Boyle were very much at the forefront of overthrowing 2,000 years of Aristotelian understanding about the world, principally by experiment. And he had a vision of matter that was atomic, kinematic, involved movement, pressure, and energy. And oddly enough, that's a story we'll come to for most of the evening. So Hooke is really here in spirit. He was curator of the experiments for the Royal Society from 1662. He became a professor in Gresham College in 1665, became a fellow of the Royal Society, and he really played a central part in the birth of the Enlightenment in the modern scientific world. So he really is a heroic figure. And in a sense, it's quite apposite to talk about him and completing his classification in some sense in the Royal Society. He was one of the founding figures in the early science there. So why return to what Hooke was preoccupied with? Well, I think we offer a small sort of completion of Hooke's vision of solids, liquids, and gases. And so it's good to understand that. And in finding some things that slide between Hooke's rules, we can look for new sorts of mechanics and new kinds of materials. So it is, I think, apposite to return to these. So let me lay out what the understanding would be from Hooke. There are two properties which define matter in the Hookean sense. They're volume and shape. So if we take a gas, it takes the shape and the volume of its container, for instance, this room. And it costs only a very little bit of energy to change the volume. You work against the pressure, but it's relatively small value. We'll return to that. And it obeys the celebrated perfect gas law, part of which bears Boyle's name from the experiments that were done with Hooke. And then if we add one property, the volume, volume's just a number, meters cubed or whatever, then we find we have liquids. And liquids have a well-defined volume. By that I mean if you want to change the volume of a liquid, you have to press on it. But a liquid will assume the shape of its container. In other words, it doesn't have its own shape. As I move this bottle around, you see the shape of the liquid changes with no problem. But if I want to change its volume, I have to work on it quite hard. And then I can take both properties, shape and volume, and then I have a solid. So a solid's got a volume and it requires some work to change it, but it's also got a shape which takes some work to change. And Hooke, as well as working on gases, he really formulated the beginnings of elasticity, saying that the force that a body will exert, or you exert on a body, depends on the extension x, and the connection is what we call the spring constant today. And this is basically Hooke's law. And so it underpins all of elasticity, and in a sense, it sort of draws all of this understanding of matter together. So this is the Hookian classification. There are two properties, volume and shape, and if you have two properties, here's the border and here's the border, you have three phases possible. So what I want to investigate tonight is there only three phases in the Hookian sense? Well, there are some things you might call a misfit, like rubber. Rubber is very soft, it's very extensible, and we'll talk quite a lot about it, but I think Hooke would say that it's a solid. It's not flowing out of my hand, it's perfectly respectable solid, at least at first glance. And then there are materials which are called liquid crystals, and they too are rather bizarre. Here's a liquid crystal. It's in a bottle because it really is a liquid. If I took the top off the bottle, I could pour it out. So it's what Hooke would call a liquid, but it does have this mysterious word crystal in its name, and that's because it's ordered in some way. And so it sort of smacks of crystal, but really in the narrowest Hookian sense, that is a liquid. So, and I want to remain in the narrowest Hookian sense. There's a plasma, which is a sort of gas of charges, which is stiff in getting the charges back and forth, but it really is a gas. The plasma will flow into a volume, and so it's a gas. And a glass is disordered in some modern sense, which we understand if we understand atoms, but this really is a solid. And it rings in exactly the way that Hooke investigated the ringing of solids 350 years ago. This is a solid. So, having disposed of these misfits, let me now turn to the misfits again and say a bit about them. So one of the things I want to talk about is classical rubber. And rubber is a solid, as you've seen. It derives, originally at least, from the latex that is the sap of a rubber tree, and it's a liquid. And if we cook and the liquid is composed of long chain molecules, which are called polymers, so that just lots of little units link together to form a long molecule. And if we bake it up with rubber, which forms these links between the chains, that's these green things, it's called vulcanization, we turn the liquid into a solid. But it's a strange sort of solid. If we take a block of it and extend it, if that's 1 centimeter or meter, and we extend it by a factor of lambda, then the chains inside, they don't flow, but they do distort, and they're like a liquid. They're in rapid motion, these molecules, but it is a respectable solid and reacts against that by wanting to retract. If we look at the shape of these molecules, on average they're isotropic, they're spherical. That's the maximum disorder that a system like this can adopt. We say that it's got maximum entropy, a measure of the disorder. And so it's rapidly moving around but on average, its shape is spherical. And if we stretch the rubber out, the molecules then elongate, and the elongated molecules are in a low state of disorder. They have low entropy. Entropy in disorder is essentially heat, as Hooke was well aware, and the heat is released as we stretch this. Nature resists that. Nature prefers states to be in a state of maximum entropy, maximum disorder, and so the rubber tries to retract in order to recover its random state. So forces are needed to extend a piece of rubber. They obey Hooke's law. They are Hookian solids. So rubber molecules are in rapid liquid-like motion. That means that a rubber is extensible like a liquid. Its molecules are in rapid motion, which means we don't have to wait for it to creep to extend. We can just stretch it. And it's got, roughly speaking, the strength of human muscle. And that's quite important. We'll come back to that. Now, the motto of the Royal Society is nullius in verba, which means don't take one's word for it, do it, demonstrate it, do experiments. And this motto goes back to the 1660s, and Hooke was in charge of experiments for the Society. And it was this idea that you didn't think about purely in the Aristotelian way about nature, but you actually put it to the test. That was the great advance that led to the modern science. So where I demonstrate during this lecture, the cue for the demonstration are these words. And now I'm going to ask my assistant to actually stretch the piece of rubber with me. And if you walk down, we can stretch this piece of rubber. It's about 2 meters long, and rubber is the most remarkable solid. Have you ever seen a solid that just extends and extends and extends? In fact, this room is not long enough. If you keep walking, and assistants are always a bit afraid of stretching too much because they think it will break, but it shouldn't break, and you could even creep back still further. So the lessons to learn from this. Firstly, this is extremely extensible. It easily stretches by 1,000%. So it's not like a normal solid, it really is a liquid. The second thing is that we didn't have to stretch it slowly so it wouldn't break. We could go at 10 meters a second and it still would have stretched. And that's fine. And clearly its specific strength is about that of human muscle. Otherwise we couldn't stretch that. The muscles in my arm are about the thickness of this rubber. And if we let it go, we see that it comes back with amazing speed. It didn't hit you, I'm sure. No. So, the moral in that is not just a big bang. The moral is that it actually can move back as fast as you like. The molecular processes are really rapid. It only goes at 10 meters a second because it's not very strong, but it is quite dense, like water. So that's what governs that. Now, the other thing is, this is very cold. If you put it to your lips, you can feel that it's cold, and that means that it's pumping heat in and out, just as we promised. So we've demonstrated that, and as Liam, our audiovisual person, remembers from school, this was an experiment you could do at school. You stretch a piece of rubber, wave it around so it lets its heat out, and then put it back quickly. You'll feel, if you put it against your lips, that it's cold, very cold. So afterwards, I'll hand some of these out to people not fortunate enough to have tried that, and you can do it for yourselves. Okay, so that is the first of our nullius in verba tonight. So let me summarize that. We have a block of rubber. It's got chains with a spherical isotropic distribution. We stretch it. The distribution, so we extend the body and we elongate the chains. So the chains are elongated. They lower their entropy. Heat is released. It's like a heat pump. You'll see afterwards. And so this is what drives rubber. The molecular shape mirrors the macroscopic shape. So remember that, because we'll return to that time and time again. And the modulus of a piece of rubber is about 10 to the 5 pascals. That happens to be 1 atmosphere. And the modulus of a rubber is just this. And for those of you who remembered the last formula, this looks like the perfect gas law. And for the very good reason, it is practically the gas law. It's all to do with entropy, like in a gas, but against shape change rather than volume change. So I hope I've convinced you that although rubber is ostensibly a solid, it behaves like a liquid, and in fact, in some senses, it's a gas. So I hope I'll leave you completely confused about rubber. Very good. Well, let me introduce another oddball, another misfit, and that's a liquid crystal. So liquid crystals were discovered about 100 years ago, and they were curiosities. They're very rich phenomena. For instance, they respond to electric and magnetic fields, but they were of no use at all until about 1970, when it became clear they could be used as displays. And they are at the heart of probably one of the largest industries in the world. 3 billion displays a year are made from liquid crystals. And that's because these are anisotropic liquids. They are liquids, they flow. I showed you a bottle of it here. And they respond to electric magnetic fields. That's what makes them a display in a watch. And they have thread-like defects in their ordering. And that gives them their name from the Greek word nemata for thread. And so when I talk about nematics, I just mean the simplest form of a liquid crystal. So a liquid crystal, it's made of rod-like molecules. So the little rods, here's a computer simulation where the rod-like elements are like lozenges. And here's a molecule that is stiff in the middle, got some junk at the ends so it doesn't crystallize, so it remains a fluid for a long time. And at high temperatures, it's just an ordinary isotropic fluid. And at low temperatures, when you cool it down, it's ordered. So the lozenges, or the little sticks, are on average ordered about a direction called the director. So these are remarkable fluids. They actually go from one phase to another as you heat and cool them. So in the spirit of this, I shall demonstrate here a bottle of liquid crystal, and I'm heating it with a hairdryer. And what you will see is that fairly soon it will start going clear, which is the hallmark of the isotropic phase. And you can see at the top it's gradually clarifying, and now you can see it's gone clear. There's a little bit of cold stuff in the middle, and now it's finally gone. And if I dip it in this water, it will speed up its cooling, and we'll see that it goes back to the cool state. You can see it's gradually going cloudy, which is this ordered anisotropic state that scatters light. That's how it works as a, can you see that? Yes. That's how it works in a display. Let me try and speed up its return. There we go. So it's now getting quite cloudy. So this is actually what's happening on the screen. Okay, that's fine. I'll put that aside and return to my talk. This cloudy phase at lower temperatures was this guy here. So these do exist, although I should reiterate, Hooke would say that this is a liquid, and I would say that as well. It's just a bit funny, this liquid. And if this experiment wasn't going to work, I have my colleagues Tim Slukins on film. Okay, so what I want to do is to try and make eventually a solid out of this, but it has to be quite a strange solid. So I want to first of all make these liquid crystals, there's the rod-like element, into a polymer, because long polymers are interesting. I hope I've persuaded you. They make interesting gases or liquids or whatever. So here we go. Here's the rod-like bit. That's these guys. These are the connectors that we connect one to the next to make a long chain. So here's some of the rods, and they have these flexible spaces at each end, and I will connect them to other rods that are not shown there. And the remarkable thing is that if I now cool these liquid crystals down, the molecules inside them start elongating. And I don't have to apply a force to elongate these polymers as I did with rubber. They just do it. So that's a very useful property. So let me summarize. extending a rubber elongates the chains, and that's resisted because it's unnatural. Orienting rods or orienting pneumatic polymers naturally elongates the chains. By naturally, I mean it just happens. We don't have to apply a force to do it. So if I've got some natural elongations, why don't I make a solid of these things and see if it does what rubber does, but doing it itself, not with an applied force. So here's the story. This is where we're aiming. I take these, remember pneumatic was the simplest liquid crystal phase that we find in this bottle. And I make a block of this by baking it up with sulfur to vulcanize it so there are the links between the chains. But now the chains, I'm just showing you the backbones, and I'm not showing you the rods that are actually causing these to elongate. So everywhere where you now see these sort of string-like objects, they've actually got these attached to them, which are doing all the action. But I couldn't draw it both in. And then I can elongate this piece of rubber by a factor of lambda from its original length of 1, and the chains will change their shape from being maybe nearly spherical to being elongated. And elongation of molecules is mirrored in extension of the body. So, now this work, as was said in the introduction, stemmed from a whole lot of theoretical physics. And I'm not going to harp on about the equations, but if there are people in the audience who are familiar with this sort of thing, then this is the free energy, which one can derive from statistical mechanics, and it's proportional to the square of the extension. And that is Hooke's law. It looks in a rather strange form because there's some other junk lying around, and these are tensors rather than just simple stretches. But basically, this is Hooke's law. So this rubber is a strange rubber, but it obeys Hooke's law in a modified kind of way. It remembers how it started, and it remembers how it currently is. But that's a technicality, and we should cast that to one side. So we take this rubber in its hot state, and we notice that if we change the order from the random state, when I heated this up with the heater, and let it cool to the ordered state, then we have molecular elongation, which should lead to macroscopic shape change. And we look at the characteristic distribution of the chains, and they're no longer spherical but elongated, and it turns out that this thing should change its length by the cube root of this anisotropy. And this anisotropy can be as much as 60. And the cube root of 60 is 4, or cube root of 64 is 4. So what it says is that as we cool this down, it should change its length by a factor of 4. Now that's a very strange thing to do. Well, we changed the length of this rubber band by a factor of maybe 10, but we were pulling on it. This should just happen by itself. So let us see that. And here is a piece of this rubber in a measuring cylinder, and Professor Terentiev is blowing hot air down it, which causes it to contract, and then cold air, which causes it to elongate by a factor of 3. So it is the most remarkable solid. We know of no other solid that does that kind of thing. Solids expand and contract a little bit, fractions of a percent, but not 300%. Now, I brought along one of these from Professor Terentiev in its measuring cylinder, but I need not a hairdryer for that, but an electric paint stripper. And the electric paint stripper has failed. So it's lucky I had the film with me. But as you can see, this is basically what you see in the film. So where I bill another demonstration, I'm afraid it won't happen. Right, now, what you've seen is that these things go up and down as we change their order, in this case by blowing hot and cold air on it, as I did with this bottle. But there's another thing you can do. You can take the rods and put some guests in the rods, and these guests are prone to bending when you shine light on them. And the molecules that do that are called dyes. I mean, we know them in that they produce color for our clothes, but dyes absorb light and they can change the structure. So these guests, when they bend, destroy the order of the hosts, and we've gone, in a sense, from the cold ordered state to the disordered state, not by putting heat on, but by putting light on. And here's a picture of these little cores here, and these are azo dyes, the classical dyes, and when they absorb a photon, then they go to a bent state, and this bend, if it's in the middle of a rod, will cause considerable disruption. And then if we go into the dark and just wait, then it will go back. We use light of a different color, and it will go back to its original state. And here is an example from another colleague, Peter Paulfy, and he's shining a green laser on this rod, and it's contracting on this side, this little bit of rubber, more than on the other side, because that's where the light hits it, and this contraction causes it to bend. And this takes place very quickly, over about 25 milliseconds. So this is, again, a very large effect, but it's optical and not heat. And here's another one, light being shone onto one of these cantilevers, causing it to bend forward. When it bends forward, it occludes the light, and it's no longer being forced to bend, it straightens up, and as soon as it's straight, then it's again exposed to the light, and it bends down again. And it happens at about 270 hertz, so it's a bit fast, and the camera doesn't follow it very well, but it's just doing this extremely fast. This is from a group in the US Air Force, and they are wanting to actually make little flying machines out of these powered by light. And that's an interesting return to Hooke. Robert Hooke was very interested in flying machines, and he found others, including a master of a college in Oxford, with whom he worked on flying machines, having started in his youth. And he writes about having artificial muscles which can power these flying machines, but we have no idea what these muscles were. They were not rubber. Rubber was not known to Robert Hooke. It was something else. Anyhow, here's a modern manifestation of this. So I've shown you some things which, although they're very unusual, large extensions, things that are driven up and down by heat and by light, we must return to Robert Hooke, because what I said at the beginning was that somehow these materials step outside the normal bounds. Well, in a certain sense, they don't, because here's one of these things, and I'm sure Robert Hooke would have said, this is a solid, it's not flowing. This is the one that we saw in the measuring cylinder of Professor Terentiev. So in what sense do they actually break this Hookian classification? So I'd like to show you this now. You remember that solids have got both shape and volume, whereas liquids have just got volume. Now volume is half a litre, it's just a number, there's no structure to that. But shape is quite a subtle business, and actually 5 numbers are required to define shape. And the nub of this story, let me press to the punchline, is when something goes from liquid to solid, we normally think of it just freezing, and that's it. But if it's something rather subtle with 5 numbers defining its shape, then it's possible that actually some of it freezes, some of these numbers freeze immediately and others don't. And so we can have something that is both a liquid and a solid at the same time. So let me try and now demonstrate this. So we take a cube, and so I brought along a cardboard cube, and it's got 3 directions associated with it, an x-axis, a y-axis, and a z-axis. So there are 3 axes that define a solid in 3 dimensions, and if I fold this in, I can now look at the distortions of this. Well, if I was to stretch this way and this way, well, each of those is, if you like, a shape change. But if I stretched it the 3rd way as well, then its volume would change. But we've already counted volume. That was 1 number, which was for a liquid. So of these 3 extensions, I must only count 2. So those are 2 of our numbers. Now, the other thing you can do with a solid is you can shear it. And by shear, I mean I do this to it. The top face and the bottom face move with respect to each other. And I can shear it like that, or I could shear it like this. up and down. So there are two numbers, if you like, associated with the shear. But let me examine this more carefully. This is what's called a simple shear, and if I do a simple shear this way and then a simple shear that way, I end up with something that looks like a diamond. Can you all see the diamond? And that's fine. That's called a pure shear, and that is a distortion of the body. But let me do it another way. I can go like this, and then I can go like that. I'm shearing downwards. And now you see something that is, again, a square. And so all I've done is rotate it like that. And that's not elasticity. That's not what Hooke would say is the distortion of a body. If I take any body, and if I just rotate it, then I haven't distorted it. The force doesn't vary like the extension as we have in Hooke's law. It's just the same as it was before. So that's just a rotation. So it says that for each of these, about each axis, this is one of them, we have shears, but I better only count one number, the one that turns it into a diamond. So we can see that on the screen now. There's simple shears added to produce a diamond, which is a pure shear. That's one number. And this is not one number. It's a shear with a negative up and down shear, and gives me a rotation. So I must count one number for each of those, and there are three different axes, so there are three numbers, and 2 plus 3 is 5. Those are the 5 numbers that define shape. So shape is not a simple quantity, and that is the let out. Now there's the demonstration, and I've already done it, so you've seen this one. That's in the spirit of the Royal Society. So soft deformations. I'm now wanting to look to see if I can deform these rather special bodies in a special way which doesn't cost anything. Deforming a body's shape which doesn't cost anything is a liquid. So can I take these solids and deform them in a special way? And so what I'd like to do is I take one of these special guys that you see in the measuring cylinder, and I want to pull it perpendicular to its special direction. Now, if this was a piece of rubber of a standard sort, when I pull it, you remember I extend the rubber, I elongate the chains, and elongating the chains is bad. I have to do work. So what would normally happen is I pull on this thing, it distorts in this direction, and it costs energy. But let me show you an alternative way to solve this problem. If I'm prepared to not only pull, but to adopt some of the diamond shape that I showed you, then the distribution of chains can simply rotate, and this continues until the pull this way is complete, and all of these guys, on average, have turned around and rotated. And they can do this because they are liquid. Liquids can deform in any way you like, although in this case, the chains are linked together and there are bounds on that. So I pull perpendicular to the director, I shear and contract and stretch all at the same time, these special shapes, and the entropy, the shape of the chains is unchanged, the liquid crystal order is unchanged, so nothing has happened. So it doesn't cost me any energy to go along here, but the thing has changed shape. So I've actually taken something that's like a solid, I've changed its shape, but it hasn't cost me any energy, at least for these very special deformations. Whereas if I'd pulled along here, or I'd pulled further along here, rotation doesn't help me, and it would have been stretched like an ordinary body. So it does both things, depending on quite how you attempt to deform it. And that is where we've deviated from Hooke. What we say is we have solids where some of the extensions don't cost energy and some do. I was going to explain this from the statistical mechanical end. Is there any enthusiasm in the audience to see these equations further? Yes? Oh, I'm delighted. Very good. So this is Hooke's law, and if I put this special deformation in there, then you will see that these square roots of tensors are annihilating on these guys, and the answer here is the unit tensor, and the trace of the unit tensor is 3. So that the energy is just 3 times a half mu, the scale out the front. And that means that the energy hasn't changed from the original rest state, And so the energy indeed doesn't go up if it's distorted in this particular way. A very special way, essentially these shears and diamonds and so on that you saw on the previous slide. And this annihilation by this guy of these memory of these tensors actually destroys the elongation this way, makes a sphere, rotates the sphere, elongates it that way. And there's a theorem to this effect that you can always do that in these sort of mobile systems. But what the underlying message is, something that is capable of stretching up and down and as a liquid is then capable via rotations of giving you this soft elasticity. They're intimately related aspects of the same phenomenon. I'm not going to be able to stretch it with a machine here in front of you, but I can show you the experimental results where if you pull perpendicular to the director, the force doesn't rise in any Hookean way until you're at the end, and then it rises in a respectable Hookean sense. So these materials are indeed not behaving like ordinary Hookean solids. And if you look at the rotations that occur as this goes on, then you find if you use this law, all of these different systems all fall on the same curve. So it's confirmation that this rather exotic-looking distortion is the thing that actually causes deformation without energy cost. So let me now conclude in the final minutes by suggesting, well, what would you do with this? Well, the most obvious thing to do is microactuation. Rubber is not a very strong material. It's a very useful material because it can store a lot of energy. We have rubber tires on our cars and not steel tires for that very reason. And it turns out that its responsiveness to light on the small scale, where you don't need huge amounts of energy, for instance, for lifting a car or something like that, is actually quite advantageous. So microactuation. But let me try and illustrate their uses by looking at some more exotic things than just moving up and down. So the first thing I'd like to show is a proposal that we've made for a solar motor. And we stretch some of this rubber, especially the stuff that can extend without force while it's in the pneumatic state. And we wrap it around a couple of wheels that are locked in rotation, illuminate one side so we get a contraction, and it starts turning. And let me illustrate that. So here's two wheels locked together in their rotation by this connection here, and we put one of these special bands like you see here around the two wheels, and we'd hang a weight off another wheel coaxial with this in order to lift it and do some work. And if we shine some light in all around here, then we'll cause this to contract, especially where it's free and no longer on the wheel. It will actually contract, and we get some force, contractile force on this side. And then as it continues around, we have this in the dark, or we let the heat out. It will then try to recover, and it gets longer, as you recall, when it's in the cold state. And so this is not so stretched, and the force is lower. So on the side where the temperature T1 is low, then the force is low, and the extension it's much elongated. And on the hot side, the force is high, and it naturally wants to contract. So we have more force on this side than this side, and this turns and lifts this weight. So it's an idea of trying to convert sunlight into mechanical energy. Now, I'm not sure that this will ever compete with solar cells, but it's interesting to try and see if we can harness energy in a new way using these new kind of mechanics. Okay, I should have completed that. This is the sense in which these wheels would have to turn because this force is greater than this one. You do, to make this work, need to make sure the two wheels are locked so that they both turn at the same rate. But their radii are different, and that's what gives you the net turning effect in this sense. So T2 is greater than T1, or this area is illuminated and this is dark, gives a difference in the forces, turns the motor, lifts the weight. Now I want to speak about one last possibility. These materials were interesting in some sense because they were ordered this way, and when I put, I should have put heat on them, they contract along their special direction by this large amount. Now, that's quite simple, but what happens if I take this privileged direction and say it's not just uniform along a strip, but it's actually in a circle? And so here we see lots of concentric circles of this ordering direction. In the jargon, these are called topological defects, and they have a topological charge, in this case in 2 dimensions of +1. That needn't detain you. There are lots of examples of this, but this particular one, it's circular. Now, if you think about it, there's going to be a serious problem. If I heat this or shine light on it, it wants to get shorter in the circumference and longer in the radius. So when it contracts this way, it expands out that way. But the contractile direction is in a circle. Now, the ratio of the circumference of a circle to its radius is 2 pi. And that indeed has been known a very long time. But now we've taken this circumference c, which used to be 2 pi times the radius, and the circumference is shrinking and the radius is expanding. The ratio of those two is less than 2 pi. And if you have a circle where the circumference is not 2 pi times the radius, then you're living in curved space. Things are not what they are in ordinary flat space. And I'll try and demonstrate that in a moment. And so there's only one way around that in this simple case, and that is that this turns into a cone, where now the radius is in the material and along here, and it's clearly much too long, and the circumference is much too short. So their ratio is less than 2 pi. And that's possible when you've got a cone. If I take a cone and put a triangle on its flank or a circle, then these are quite ordinary. There's no tricks there. But if I let the circle be punctured by the tip of the cone, then this ratio of the perimeter to the radius is no longer right. And what that's saying is that there's a source of curvature of space. It happens to be localized at a point, for a rather simple example of a cone. So people think of cones as being in flat space, but in fact there's a point in a cone which is not in flat space. So I thought I would demonstrate this again in the spirit of this institution. And here is a disc, and I'm going to turn this into a cone because I cut it, and that allows me to take up a lot of extra length. Can you see the cut in the... And so if I take this cone and put it over this circle and put it over itself, I can turn it into a cone. And here you see it as a cone, and the triangle that was on the surface of the cone is a perfectly ordinary triangle, and the angles in it are certainly not changing as I put it on the flank of a cone. There's no tricks at all. However, if I turn this over, I've drawn a triangle here which will be punctured by the tip of the cone. So let me then put this over itself, and I take up this and I keep on squeezing it up until they meet. And now we've got the two original angles which I've marked of the triangle there as they were before. But this third angle is an oblique angle, greater than 90 degrees, but the third angle was originally an acute angle, less than 90 degrees. So the angles on this triangle now add up to more than 180 degrees. That's the case when you draw triangles on the surface of a sphere. A sphere, the surface of a sphere is also a curved space, and the usual rules of Euclidean geometry go away. So this is an example that you can do yourself at home. So indeed, if we do this, then this is an example of a cone where the perimeter is too short for the radius. And if we do the opposite, then actually the circumference is too long for the radius, and it crinkles up. And these are what you might call anticones. And anticones come in varying degrees. They're sort of quantized in a sense. And the number of wiggles up and down is 2, 3, and 4. And you can do experiments on this, and indeed you find that stuff that is like this, you heat it more, it becomes more and more of a cone. And those of you who are into curved spaces, then if the contraction is lambda and lambda to the minus nu in the perpendicular direction, the radial direction, then the curvature is just this. So we can relate the curvature of these spaces to the contractions that we see along the directors. So I want to conclude by one last example. What we've just seen is how this sort of mechanics can change the curvature of space. And that has a lot of interesting applications, not just theoretical. But we can try and do something else. If we arrange these ordering directions in this sort of way here, this is utterly incompatible. If these were to contract along these black lines as we illuminate it, then it will just fracture. Unless we do what we did on this cone, we cut it and exist with cuts. So let me show this. If we now shine light on this, then these things here, if these open up, this can remain a flat sheet without fracturing. So we've done something different. This mechanics has led to a change in the topology, that is the number of penetrations of the space, rather than the curvature of the space. And these angles change by amounts that you can calculate from the mechanics. So why would you want to do that? Well, we believe that this could be a photo-operated filter. The trouble with filters is they capture what you're supposed to be filtering, and they clog. And if you can change the hole size in a filter, then you can flush the stuff out and start again. The other thing is that if these angles are small, which we can easily make small, and these cuts are short, then we can get openings here which are in the nanometer length scale. So we can filter quite sophisticated things like DNA and so on. So that this is a nanometer type sieve, which is variable according to the light we shine on it. And I conclude with an array of these things made in the way of the previous slide. And here are some candidates to open at the vital parts of this arrangement. And as we shine light on it, then these open up, these slits, and here you see that they're open. A bit hard to see, but I've blown it up here. So this would be an example of a material which changes its topology as we turn light on it. So you might have thought that I was abandoning my hero Hooke in trying to relate things that sort of break his rules, but not at all. Hooke's rules are still fundamental. They still delineate solids, liquids, and gases. It's just that some of these solids are a little bit peculiar, and from them you get some new mechanics, and you get optothermally driven distortions. You get soft elasticity, this new kind of force-free thing that I was showing you. And if you do it in a non-uniform way, you can get curvature and topology changes. And of course, with these rather interesting effects, we'd like to search for some new applications. And I've only hinted at where this search is leading. So thank you for your attention.
I'm delighted that Professor Warner is going to be able to take some questions from you this evening. We do have a couple of my colleagues here will be have microphones, so if I can ask if you can wait till the microphone gets to you. Who would like to ask a question?
Everyone is totally baffled.
Indeed. Yes.
Oh, yes.
I think this shows my ignorance. But when you had the example of the rod that bent,
Yes.
what I couldn't quite understand is why it bent in one direction. Why wasn't everything struggling? Each particular molecule thing wanted to go in its own direction, and the result was you didn't get any consistent movement in one direction.
So let me just go back to what I think you're thinking about. Are you thinking about this one? Yeah. So this, when I described it as a rod, was perhaps a slip of the tongue. This is a strip of rubber. And in it are these sort of rods that make it up. And the reason that it bends in one unified way is that the light strikes this upper surface first and absorbs in order to create this bending at the molecular scale, so that the light, by the time it gets through to the other side, is rather weak. So if we take a cantilever and cause the top to contract more than the bottom, then it's bend. And so it's macroscopically bending. Now, I did use the word rod at that point, and I really didn't mean rod. I meant a cantilever or a strip.
Anybody else? Gentleman there.
What happens at the atomic level during all these contortions? When you're compressing liquids,
the answer is
solids, etc.
The answer at the atomic level is very little. So if I take this piece of rubber, the chains are stretched, but they don't. All they do is all of their random configurations. Not all of them are accessible, and they are on average a bit stretched out. But you don't pull on them like you do on a diamond. If you try to stretch a diamond, you are stretching at the interatomic bond level. Here, almost nothing happens. It's a very weak effect. And so this rubber changes its shape, and it changes it at constant volume. All rubber deforms at constant volume. So when I elongate like this, it contracts in the other directions. You can see it here, actually. You see the width that way gets smaller. And that's a signal that very little is happening at the molecular level. We're simply biasing the sort of gross molecular conformations. That's why rubber's so weak, but it's also why it's so extensible.
Sorry, I'm just don't really understand why when you cool it, the liquid crystal, it points in one direction like that.
Well, that's a very good question, and I didn't really explain why that should happen. But in general, with matter, when you cool it, it adopts a more ordered phase. So if we take liquid water and we cool it, it forms a nice crystalline array, which is ice. And so what the liquid crystal can do is order as best it can. And its only scope, really, apart from forming a crystal, is to actually get these rods and make them parallel to each other. And so it's a lower temperature, higher order, lower entropy phase. It basically, it has much more, once it cools down and its motions are not so fast and so random, it's got more chances to actually explore space if they're aligned. Think of matches in a matchbox. When they're constrained enough, when you have a lot of matches in a matchbox, then they're always parallel. You don't find them in any old direction. It's the same with these molecules. Yes?
Hi. I was just wondering, these materials, they're not found in nature, I take it. They're man-made. How did the material scientist or chemist that decided to make one know where to start in making something like this? Did they know what they were expecting to get at the end of an experiment, or was it serendipity that it just happened, or how did these things come about?
A bit of both. There was a very great physicist called de Gennes, a Frenchman, who was my PhD examiner as it happened. And he envisaged this quite a long time ago, about 10 years before they were actually made. Then they were made, and at about the same time, we theoretically had this funny form of Hooke's law we came across. And we discovered theoretically that actually there were these strange distortions you could put in that didn't apparently change the energy. And that we didn't believe at first, because it broke Hooke's law, and we thought that is just not on. After several weeks of prodding this mathematical formula, we concluded that actually it was right. And people did experiments in Germany initially, and then in Cambridge, where they demonstrated that this actually occurred. Now the rubber, the light emitting one, the light responsive ones, that really was serendipitous. We predicted these in Cambridge, and I went to my colleague in Freiburg in Germany, who had done a lot of the original work, and said, look, this should happen. And he said, oh, we've made those before, but they don't apparently do anything. And this was not very gratifying, but what it turned out was that they were resting on the windowsill. And when the sun came out, they contracted, and that's what they saw. And in the night, when they were away, they elongated, and it just wasn't known. So they actually looked at them much more closely, and we eventually published both the theory and the experiment together. But actually, the theory and the experiment were quite separate, and several years didn't know about each other.
I think we have time for one more question.
There's one down there, along the aisle.
Hi. You mentioned the mechanical motor you had with light on one end and a cool other end. And you said you thought that it might be less efficient than a solar cell. How much less efficient than a sort of machine powered by solar cells do you reckon the machine you showed us would be? And have you made one? Have you tried?
Well, what I said actually was, I mean, it was a reasonable presumption from my caution on this to say that it wasn't as efficient. I think it could possibly be quite a bit more efficient. But the problem is that really, if you have some sort of solar cell out in the desert, you just don't want any moving parts. And so, although it may be more efficient, it's probably less desirable. Mechanical things on the whole you don't want to know about. You just want to, just dust them down every few months, but otherwise don't be worried about it. So my reservation is more that than it's not very efficient. We believe the efficiency could be maybe 20, 25%. It depends how you make them, and we're investigating at the moment a sort of mechanical turbine to try and optimize the efficiency. And people are thinking about how to make them. They've made crude ones already which move rather slowly, but we think that we can make much better than that. So there are some small strips of rubber here, and those who haven't seen this before, they're welcome to come and take these away. And there's even one of these, so you can come up afterwards and take these with great pleasure.
Thank you. I'm sure you'd want to join me in thanking Professor Warner.
Good of you to stand in between.